properties, physical and chemical properties of carboxylic acid. So as I told you, physical properties means this is based on, means depends on what is the solubility, depends like that. Got it? What is the solubility of the compound? What is the boiling point of the compound? Then what is the nature of the compound? If it is solid, liquid, gas, that is a physical property. So we are going to the physical and chemical, both properties we will discuss in this chapter. First, we are moving to physical properties of carboxylic acid. Okay? See. At normal temperature, aliphatic carboxylic acid with 9 up to 9 carbon atoms are colorless liquids with disagreeable odors. Okay, see, aliphatic means normal, not the ring. Okay, aliphatic carboxylic acids with up to 9 carbon atom. Up to 9 carbon atom means till, means maximum. Normally we can attain till 9. Above 9 is also possible. But maximum till 9 carbon atoms, the carboxylic acids containing up to 9 carbon atoms are colorless liquids with odd liquids. Okay. Because of their low volatility, the higher acids are wax-like solids that are visually odorless. See, in case of the boiling melting point, then the solubility of the alcohols, and that one we discussed in the last class, right? So in that time, I told you, they have, when the number of carbon atom is increasing, or when the molecular mass is increasing, their boiling point is increasing. When the branching is increasing, it is decreasing. When the chain length is increasing, the boiling point is increasing. Why? Because when the chain length is increasing, there is a maximum. You remember, I told you, I drew that diagram, like means there is a maximum contact points between the adjacent molecules. So the, if you want to convert them into liquid, you have to break all that contact points. So between propane molecule, only 3 contact points will be there, because propane contains 3 carbon. Between pentane, there will be 5 contact points, right? Yes. Same thing is here. Normally, till 9, it's, I told you, it's liquid. When number of carbon atom is increasing, the same thing. The contact points means the interaction between the adjacent molecule will increases, right? When this interaction is increasing, what will happen? When the interaction between the molecules are increasing, they will be close together. Close together means they will exist as solids. Okay? When they are close together means they are existing as solids. Okay, understood that contact point thing? Means I already discussed in the previous classes. Means see, suppose I am taking ethane molecule. Ethane molecule means I am taking 2 ethane molecule. So there will be between the molecule, there is a points of contact, means 2 points of contacts are there. This is not covalent bond, ionic bond, or any other normal intramolecular bond. This is intermolecular interaction. Okay, so if you want to convert this particular compound into, means suppose this is in liquid form. If you want to convert into normal vapor form, you have to break 2 bonds here. At the same time, you are taking propane, pentane. Pentane means it will be 5 carbon, CH3, CH2, 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 CH3. So if you want to break the force of attraction between pentane molecules, what you have to do? You have to break the force, 5 force of attraction. See here, 5 points of contacts are there. So when these points of contact increases, the attraction between them is increasing. They are normally existing in solid form. Okay, that's why when the number of carbon atom is increasing, their solid means they have a tendency to exist in solid form, means wax-like solids. The nature is like that. Okay, yes. Carboxylic acids have a greater boiling point than comparable molecular mass aldehydes, ketones, and alcohols. See, aldehydes, ketones, all of them contains carbonyl group. Alcohols contains OH group. If you are comparing the boiling points of these compounds, carboxylic acid have higher boiling point. Why? See, due to the extensive carboxylic acid molecule interaction via intermolecular hydrogen bonding. Then you will have a doubt, I know. Because between alcohol molecules also there is hydrogen bonding, right? Then why the carboxylic acids are so special? The thing is, more extensive carboxylic acid molecule interaction via intermolecular hydrogen bonding. Extensive. Why? See, if you are taking one carboxylic acid molecule, this is another one. See, here we have two carboxylic acid molecule. Then within the molecule, you can see two hydrogen bonds. Got it? One carboxylic acid molecule can produce two hydrogen bonds. See, this is one carboxylic acid. Using the oxygen, they can produce one hydrogen bond. Using the hydrogen also, they can produce another hydrogen bond. Got it? If you are taking normal alcohol, CH3OH, okay? Then I am taking another alcohol, CH3OH. But here the interaction is only one. Okay, but here at a time, one molecule can produce two hydrogen bonds. They are existing as a dimer. What is dimer? See, two molecules are existing together. That is called a dimer. Okay, so this is called a extensive hydrogen bonding. Extensive intermolecular hydrogen bonding. This is not present in aldehydes or ketones or alcohols. This is only present in acids. So even the alcohols contains hydrogen bonding, but the carboxylic acid have comparatively high boiling point because this hydrogen bonding present in carboxylic acid is more extensive. Like this one. Okay? Yes. In vapor phase, the hydrogen bonds are not entirely broken. In fact, most carboxylic acids occurs in vapor phase or in aprotic solvent as dimers. See, normally I told you till 9 carbon atom, they are existing as which state? Liquids, right? More than 9 carbon atoms, they will normally existing in solid form. They are wax solids, like that. Okay. Then, in case of carboxylic acid, if you are converting the liquid carboxylic acid into vapor form, even there will be an interaction, means the hydrogen bonding. Why? Because there is two hydrogen bonding per molecule. When you are converting, see, what is boiling and melting? We are breaking the force between the molecule. So if you want to convert this particular acid into vapor, you have to break the two bonds, right? Then only they will convert it, then only they will be free. They will be converted into vapor form. Okay, but what is the difference here? Here the bonding is extensive, so it is not possible to break the complete bonds. Still, in vapor phase also there is a means little force of attraction will be there. Hydrogen bonding will be there between the carboxylic acid molecule. In vapor phase also there will be a little hydrogen bonding interaction between these molecules. That's why they are existing in stable form. Okay. So normally all the molecules are forming one hydrogen bond, but in the carboxylic acid it is more extensive. They can form at a time, they can form two hydrogen bond. That's why that is called extensive. That's why they are existing in dimeric form. Okay. Yes. Simple aliphatic carboxylic acid with up to 4 carbon atoms are miscible in water due to the creation of hydrogen bonds with the water. Same thing. I told you physical properties means we are dealing like these properties, means solubility, boiling point, like that. So simple aliphatic carboxylic acid with up to 4 carbon atoms are miscible in water. Miscible. What is miscible? Miscible means they are mixing, right? I told you in the last class, right? You remember? Miscible means they are mixing. They are mixing together. Okay, so the aliphatic means normal chain, not the ring structure. Okay, up to 4 carbon atoms are miscible due to the creation of hydrogen bond. I told you alcohols are miscible in water. They are soluble. They are miscible with water, right? Why? Because they can form hydrogen bond can be formed between the alcohol molecule, and the hydrogen bond can also formed between water and alcohol molecule. How? Because the alcohol is there, ROH is there. If you are taking water molecule here, this one can interact with the oxygen. That's why these alcohols are miscible in water. The same type of interaction you can see in carboxylic acids also. But the thing is up to 4 carbon atom. The carboxylic acid means still butanoic acid. Okay. So the butanoic acid means propanoic acid, ethanoic acid, all of them are soluble in water. Why? The same reason. R, C double bond O, OH. So I am taking one water molecule. So what will happen? This one can make hydrogen bond with the hydrogen. Okay. So this is the hydrogen bonding interaction. That's why they are soluble in water. They are miscible with the water. Higher carboxylic acids are practically insoluble due to the enhanced hydrophobic interaction of the hydrocarbon component. What is the hydrophobic interaction? We have two types of interaction. They are hydrophilic interaction and hydrophobic interaction. What is the difference between hydrophilic and hydrophobic interaction? Philic means loving. Hydrophilic means water loving. Hydrophobic means water hating. Okay. So the higher carboxylic acid means the carboxylic acid containing more than 4 carbon atoms are insoluble in water due to the enhanced hydrophobic interaction of the hydrocarbon component. See, normally I am writing RCOOH. Right? So this is the hydrophobic end. Hydrophobic end means water hating end. Okay, so this hydrocarbon component have hydrophobic interaction with the water. They have less tendency to mix with the water. They won't mix with the water in greater extent. They have less tendency to mix with the water. That is hydrophobic nature. That's why these, because when the number of carbon atom is increasing, the chain length is increasing. The COH group is still remaining same. Or suppose all the acids are containing only one carboxylic acid group. But this R group will change, right? Means R group will be means more than 4. 5 maybe there, 6, 7, 8. Any number of the carbon atom will be there in the hydrocarbon part. So when the number of carbon atom in the hydrocarbon part is increasing, the hydrophobic interaction is dominating. Hydrophobic interaction dominating means they are not liking to dissolve in water. Okay, that's why these higher carboxylic acids are less soluble in water. Got it? Yes. In cold water, benzoic acid, the most basic aromatic carboxylic acid, is practically insoluble in cold water. See, remember, in cold water, not the ordinary water or hot water. In cold water, benzoic acid, the most basic aromatic carboxylic acid, is practically insoluble. Okay, memorize. Carboxylic acids are also soluble in less polar organic solvents such as benzene, ether, alcohol, chloroform, and others. Okay, not only in water, they are soluble in less polar organic solvent. Not all less polar organic solvent, in some less polar organic solvent like benzene, ether, alcohol, chloroform, and like that. Got it? Yes. So that is the physical properties of carboxylic acid. Next, we are moving to chemical properties. See, physical properties means simple, just theory only. How they are making a bond with the water molecule, how they are making bond between them. Then what is the nature of that bond, right? How that nature of bonding is affecting their properties. But chemical properties are not like that. Chemical properties means how they are reacting. Okay, how they are reacting with the water, how they are reacting with the metal, base. Got it? They are the chemical properties or chemical reactions of these compounds. Okay, see, first one is reaction with metals and alkalis. Reaction with metals and alkalis. How these acids are normally reacting with the metal. I am taking one acid, CH3COOH, one acid. Okay, then what is the reaction here? Similar to phenols, carboxylic acids evolve hydrogen with electropositive metals and create salt with alkalis. See, here the acid they took, RCOH. R group may be any group. Whenever this acid is reacting with a metal like sodium, what will happen? This hydrogen will be replaced by sodium. Why? CH3COOH, right? This one will decomposes to CH3COO minus plus Na plus. Got it? CH3COO minus plus, sorry, not Na plus, H plus. Got it? So what will happen? This hydrogen ions and this is called a carboxylate ion. Carboxylate ion. Normally, carboxylic acid will ionizes into carboxylate ion and H plus ions. So when this acid is reacting with a metal, what will happen? This H plus ion, first they will undergo ionization. On ionization, they will produce this CH3COO minus ion and H plus ion. Then this CH3COO minus ions will react with the metal ion and produces COON. Means this hydrogen is replaced by the metal sodium. Whatever the metal, the same reaction will take place. Then here you are taking two molecules of acids, right? Then what will happen? From each molecule, one H plus will be removed. So that H plus ions will combine together to produce hydrogen molecule. Okay, they are getting electron from the sodium, then the H plus ion will convert into hydrogen atom. The next H plus ion will convert into hydrogen because sodium, in order to combine with the COO minus ion, sodium have to lose one electron. Then sodium will produce Na plus ion plus one electron. This one electron, this H plus will accept and convert into hydrogen. Got it? Then the two molecules, this will undergo the same reaction. Then two hydrogen atoms will be produced. They will produce hydrogen molecule. Got it? Okay. So this is the reaction. See, next one. Here we are reacting the acid with the metal, right? Now we are going to react the acid with the sodium hydroxide, NaOH. How will you react the acid with the sodium hydroxide? Same reaction. See, listen. The sodium hydroxide will convert into Na plus and OH minus. Okay. So this RCOOH group decomposes to same thing, RCOO minus plus H plus. Then this RCOO minus will react with this Na plus ion and produces RCOONA. This remaining H plus and this OH minus ion react together to produce water. Okay. This is the reaction with the base. So this is the reaction with the metal. This is the reaction with the base, means an alkali. Next, I am taking another alkali. Sodium bicarbonate. Sodium bicarbonate means NaCO3, right? Same reaction. See, the acid I am taking is RCOOH. They will convert into RCOO minus plus H plus. Same reaction. Then what is happening to sodium bicarbonate? NaCO3 will convert into Na plus plus HCO3 minus. Okay. Then next step, same thing. RCOO minus will react with Na plus. Why? Because this negative and positive, right? See, So they will convert into RCOO minus react with Na plus ion and produces RCOO Na. Okay, so the sodium salt of acid, you got it, right? Next one, the byproducts are water and carbon dioxide. How you are getting this water and carbon dioxide? See, HCO3 minus is there and H plus is remaining here. From HCO3 minus, they will produce carbon dioxide. So one carbon and 2 oxygen removed. Then remaining 1 oxygen, this hydrogen and this hydrogen, they will combine together to produce what? Okay, so this is the reaction. So the 3 reactions. See, anyway, whatever it may be, acid or base means alkali or any other thing, the same thing is producing. That is sodium carboxylate. Whatever suppose you are taking acetic acid, you will get sodium acetate. If you are taking propanoic acid, you will get sodium propanoate. Okay, whatever the acid you are taking, you will get corresponding salt, sodium carboxylate. Okay, the reaction is hydrogen is removing, the sodium is linking to the remaining ions and they will produce RCOONA. Okay, this is the reaction with the metals, bases and the formation of these ions. Okay, then next one, effect of substituents on carboxylic acid acidity. Carboxylic acids are acidic in nature. Why? Because they are acids. They can release H plus ion. See, in every reactions, I wrote the same reaction. RCOOH is producing RCOO minus plus H plus. Means they are releasing H plus ion. H plus ion donors are acids. H plus ion donors are acids. Okay. Substance can change the stability of the conjugate base and hence the acidity of the carboxylic acid. Normally, carboxylic acid, they can donate H plus ions. So they are acidic in nature. But the substituents can change the stability of the conjugate base of the acid. What do you mean by the conjugate base? What do you mean by conjugate base? See, here, when this acid is decomposing, see, you know weak acid and weak bases, right? You studied about the ionic equilibrium in grade 11. So ionic equilibrium is the equilibrium exists between the ions. So RCOOH will convert into RCOO minus plus H plus. RCOO minus plus H plus ion. This is a reversible reaction because these organic acids are weak acids. Organic acids are weak acids. Weak acids means they are not completely ionizing. They will combine together to produce the acid again. That is a weak electrolyte, right? What is the difference between weak and strong electrolyte? Strong electrolyte means they will completely ionize. They will completely dissociate. Strong. Weak means they will incompletely. They won't completely ionize into the ions. They will come back. They will combine together to get the acid again. And not only acid, whatever the base it is, the same thing. So weak electrolyte means weak bases or weak acids means the original compound that you are taking. Okay, so here see, when this the tendency of this acid to release this H plus ion is decreasing, the acidic strength is decreasing. That's why this the first point indicates, see, when the substituents are coming there, when the substituents are not releasing, the means the substituent is not allowing this particular acid to release this H plus ion, the acidity will decrease. Okay, suppose a substituent is coming to this acid. That substituent is holding this H plus ion. They are not allowing this H plus ions to leave. Means the acidic property is decreasing. Next one, see this one, conjugate base, right? Yes. See, conjugate base means I told you they will combine back to get this acid together. So this is the acid and the substance you are getting RCOO minus. So I told you acids are H plus donors. Then what is bases? Bases are H plus acceptors. See, what is the backward reaction here? This RCOO minus will take the H plus ion and convert into acid. So this RCOO minus ion is acting as base because bases are H plus acceptors. This RCOO minus ion will take the H plus ion to convert into acid. So this is the acid, this is the base. This base is called a conjugate base. Conjugate base. Why this is called a conjugate base? Because this base is forming from the acid. So this is the RCOO minus is the conjugate base of the acid, whatever you are taking here. That's why we are using the term conjugate base. Okay, see, electron withdrawing groups improve the acidity of the carboxylic acid by stabilizing the conjugate base via negative charge delocalization via inductive or resonance process. See, suppose I told you whenever a substituent is coming to this acid, depends on the nature of the substituent, the acid strength we can predict, means they will change, right? Suppose the acid coming is not allowing the H plus to leave, then H plus ion is not leaving properly, means the acidic property is decreasing. Okay, so when electron withdrawing groups is there, electron withdrawing group means, suppose an electron withdrawing group, suppose an X, I am adding an electron withdrawing group X here. So what will happen? Electron withdrawing means they are taking the electrons. Okay, they are taking the electrons means, see, R, C, O, OH. So we have to release this H plus ion, then only it will be acidic. We have to release this hydrogen as H plus ion. So when an electron withdrawing group is coming here, what will happen? They will take all the electrons. So the electrons will move to this side. Electrons will move to this side. At the same time, hydrogen is not moving to this side. Only the electron withdrawing group is there. So the electrons are moving to this side. Then what will happen? This hydrogen will easily remove as H plus ion. What is H plus ion? Hydrogen is not taking electron. Hydrogen is leaving the electron there, and hydrogen is leaving as H plus ion. H plus means they are not taking the electron. All the electrons are moving to this side, means hydrogen, it is easy to remove the hydrogen as H plus ion. So if an electron withdrawing group is there, they will increase as the acidic strength of carboxylic acid. Means when an electron withdrawing group is there, it becomes easy to remove the H plus ion. Okay, by stabilizing the conjugate base via negative charge on delocalization via inductive or resonance process. Same thing. Resonance we discussed, right? Yes. Next one. Electron. Then see, what is the stabilization of this conjugate base? The same thing. This H plus is removing easily, means they are not combining with the CO. They will combine, but the combining tendency will be less. Means the reverse reaction tendency will be less here. Because electron withdrawing group is there. So electron withdrawing group is taking the electron, hydrogen is removing as H plus, then this ion is formed. Which ion? RCOO minus is formed. That RCOO minus is not taking the H plus ion again, means the forward is not taking, means that much fast. Why? Because this RCOO minus ions are stable, because some of the electron withdrawing groups are stabilizing this ion. Okay, that's why they are stabilizing this conjugate base and it increasing the acidic property. Then electron donating groups. What is electron donating groups? Means I told you electron plus psi groups, right? Means I like alkyl groups. We discussed about that in during the stability of carbocations, right? Yes. So plus psi group, so electron releasing group means they will push all the electrons towards the COO group. Suppose R COOH. Suppose any electron with donating groups are there, electron releasing groups are there, they will give all the electrons towards here. So see, here we have to release this hydrogen as H plus ion. But what will happen if all the electron density is coming here? That electrons have negative charge, right? Electrons are negatively charged. Hydrogen is here trying to remove as H plus ion. So when the electron density is moving towards this oxygen, that electron density will attract the H plus ion because opposite charge. So this electron density is attracting the H plus ions, means they are not releasing these H plus ions easily. What it means? Acidic property is decreasing. Means they are destabilizing the conjugate base. Means the ion forming RCOO minus is not stable here. Why they are not stable? Because of this plus I group effect, the electron density is here. So they will always attract the H plus ion. Means the H plus ion is not leaving properly. Means they are, if the H plus ion is leave, then only this RCO minus will be stable. So this effect will destabilizes the H plus with RCO minus ions. Got it? Yes. So that is the destabilization and stabilization. Okay. The direct attachment of the group such as phenyl or vinyl to carboxylic acid increases the acidity. Why? See, contrary to the expected decrease owing to the resonance effect illustrated. See the same thing. Okay, this one. This is due to the higher electronegativity of the sp2 hybridized carbon atom to which the carboxyl group is connected. See, if we are comparing sp3, sp2, sp hybridization. In sp3 carbon, the S character is 25%. The remaining 75% is P character. In sp2, 33% is S and the remaining 66 is P. In sp, it is 50-50. So comparing to sp3, sp2 have more S character. What do you mean by this more S character? Means they are more connected to, means they are more close to the nucleus. So they will attract the electrons. Okay, so the direct attachment of the group such as phenyl or vinyl carboxylic acid increases acidity contrary to the, this one is clear, right? Yes. Next point you see, this is due to the higher electronegativity of the sp2 hybridized carbon to which the carboxyl group is connected. Okay, yes. The presence of electron withdrawing group on the phenyl of an aromatic carboxylic group. The same thing, see here. Okay, here pK is comparatively, when it is pK is increasing, acidic property will decreases. Okay, so the electron withdrawing and the electron donating effect is clear, right? Yes. Next one. Next thing is reactions involving cleavage of carbon OH group bond. See, in every chemical reaction, the bond should be break, right? See, COOH group. So here the reaction means involving the breaking of this COH bond. We have to break this bond. Okay. See, first reaction is, so we discussed about the preparation. Now we are discussing the properties, chemical properties of acids. Okay. When carboxylic acids are heated with mineral acids such as sulfuric acid, then phosphorus pentoxide, it produces appropriate anhydride. What is anhydride? See, here I am taking acids, right? Two same acids I am taking. You can do this reaction with the different acids also, no problem. Okay. Then they will see what is happening here. Cleavage of OH bond means COH bond. So here what is happening? See, here one water molecule will be eliminated. See, here the COH bond is breaking here. Okay, so what is the remaining things? CH3 is there, C double bond O is there, this OH is removed, this hydrogen is removed and the oxygen is there. It is connected to the remaining group like this. Ethanoic anhydride. Okay, so this is the reaction which we are removing water. Why we are using concentrated sulfuric acid? Sulfuric acid is a dehydrating agent. Means they can take the water present in a particular compound. Okay, so this is the formation of anhydride. So in the formation of anhydride, they should break the bond between carbon and hydroxyl group. Okay, yes. Next one is esterification reaction. We know that we already discussed about it, right? See, RCOOH react with RCH2OH. Okay, so what will happen? Same thing I told you. You remember OH group from here, hydrogen from here is removing. See here which bond we are breaking? The bond between this carbon and see this OH group. We are breaking that one. Okay, so this is the esterification reaction. So in esterification reaction also we are breaking COH bond. Same thing in anhydride formation, the water molecule is removing. In esterification reaction also water molecule is removing. But in normal, anhydride reaction, we are taking two acid. Here we are taking one acid and one alcohol. What is it? That is the difference. Okay. Yes. Next one. Mechanism of this carboxylic acid esterification. Mechanism of this. We have to know the mechanism also. Okay. See. The esterification of carboxylic acid with alcohol is a type of nucleophilic acyl substitution. Nucleophilic substitution, what is that? We know, right? Yes. Protonation of the carbonyl oxygen activates. See, this is the carboxylic acid. So what is the first step? In an acidic medium, protonation. What is protonation? This H plus ions will be added to this oxygen. That is protonation. See, protonation of the carbonyl oxygen. This is the carbonyl oxygen. Protonation means we are adding proton to this carbonyl oxygen. Okay. Now, what is the product you are getting? When this H plus is added here, it will be RCOH, no change. And this O will convert into OH group. Okay. Then, hydroxyl group is converted into OH2 group by the proton transfer in the tetrahedral intermediate. I told you. Which is removed as a neutral water molecule due to the superior leaving group. See, here, what will happen? I am taking another alcohol molecule. So this is esterification. Esterification means we have to take an alcohol, we have to take a water. See, I will explain with an example. CH3, COOH. This is ethanoic acid. So protonation means I told you the H plus C. H plus means there is no electron, but on oxygen there is lone pair of electron. So this H plus ion is making bond with the oxygen. So what is the product? I will write the product here. Okay. CH3COH. No change in this one, but this one will convert into OH plus. Because this is H plus. So the H plus we have to write because this oxygen is using this their electron pair to form bond with this H plus ion. So the acid is used. Next one, esterification means we need an acid and alcohol. Okay. So next I am taking an alcohol. Suppose I am taking CH3OH. On oxygen we have a lone pair of electron, right? So what will happen? The reaction happening here is using this lone pair, this molecule will attack the carbon. Normally around carbon atom 1, 2, 3, 4 bonds are there, right? When this alcohol molecule is attacking this carbon, this bond become 5. Obviously it become 5. Then in order to make it 4, one bond will move here. Okay, so what is the product? CH3, C, OH is still there. Then OH. Why this double bond is moving here? So this positive charge will be, see, this double bond will neutralize this positive because one pair of electron is retained on oxygen atom. Normally oxygen was used to one pair of electron to make bond with this H plus ion. Now when this double bond is moving to oxygen, yes, that electrons are retained. Okay. So So what will happen? This is the product you are getting. Then next one, this O is O group oxygen, the CH3 is there, and this hydrogen connected to oxygen is this one. Still one lone pair is there because they have two lone pairs oxygen. Okay, this one. Got it? Yes. Then what is the next step? What will happen? The same thing will happen again. See, proton transfer. This is a reversible reaction. See, these electron pairs will come here. Then this OH will remove. Okay. Then here you will get OH group. Here you will get the remaining group, OR group. Understood, right? Any doubt? Any doubt? See what is happening. CH3COH, then COH here. Okay, then this is the OH group. Then what will happen? One of the lone pair of electron from here, it will transfer to here. Then this OH will be removed. Then I told you this bond will also go here. Then this OH and this hydrogen combines together to produce water. Then what is remaining? CH3, C, double bond OH. Again positive charge will come because this double bond is moving here. This is resonating structure. Then the remaining is OR. Okay. Then this is not ester. Ester is RCOOR. So here instead of R, I am taking CH3. Okay, don't be confused. CH3. Okay, RCOOR. Now we have to convert this compound into this compound. How? This hydrogen can be removed as H plus ion. Okay, when this hydrogen is removing as H plus ion, they will release the electron. That electron will come here. Then you will get the product CH3, C double bond. No change in double bond. Then the hydrogen is removed. Then OCH3 is still there. This hydrogen is removed as plus H plus. This hydrogen. Okay. This is the mechanism of esterification reaction. Okay. Next one. Reaction with PCl3, PCl5 and SOCl2. How these carboxylic acids are reacting with phosphorus trichloride, phosphorus pentachloride and sulfonic chloride like that. Thionyl chloride like that. Okay. See. Carboxylic acid, hydroxyl group reacts similarly to alcohols and are easily replaced by chlorine. See, this reaction you have to memorize. Acid reacting with the PCl5, RCOCl plus POCl3 plus HCl. Okay, how? This is RCOCOH, right? Suppose I am writing CH3COOH reacting with PCl5. Now, this OH group will be removed and one chlorine will come here. Then what you will get? CH3, C double bond O, Cl. Plus, this hydrogen is removing. That hydrogen react with, here see, one chlorine we used here, remaining 4 chlorine. One of the chlorine react with this hydrogen to produce HCl. Plus, oxygen is remaining here. Phosphorus here, 3 chlorine here. So they will form POCl3, the first reaction. Okay, next one, second reaction. The similar reaction. See, what is the difference? RCOH reacting with the PCl3, but here we are taking 3 molecules. So RCOOH react with the PCl3 and produces C. Here, the OH group will be replaced by 3 chlorine because I am taking 3 molecules. So, in each molecule, 1 chlorine will go. So, you will get 3 molecules of RCOCl. Plus, 1 phosphorus is remaining. From this molecule, 3 hydrogen and 3 oxygen is removing, right? So, it will be H3PO3, phosphoric acid. Okay. Yes. Because we are taking 3 molecules. Don't forget this one. 3 molecules. Here in the first and third case, we are using only 1 molecule. Okay. Next one. SOCl2, thionyl chloride. RCOOH react with SOCl2. Same thing. OH is replaced by 1 chlorine. RCOCl. Now, 1 oxygen removed from here react with SO and produces SO2. Remaining hydrogen and 1 chlorine react with it to produce HCl. Okay? Yes. Simple. 3 reactions. Okay. Next one. Reaction with ammonia. Carboxylic acid react with ammonia to form ammonium salt, which are then heated to high temperature to form amides. Important. See the reaction. Okay. See, in this reaction, you can see this is the acid and this is the ammonia. So this acid is reacting with the ammonia. See, this acid is reacting with ammonia and produces, see, ammonium acetate. This is ammonium acetate. Okay. See, acid react with NH3 means ammonium acetate means NH4 plus group will be there. Okay. Means nothing is eliminating. They are directly combining. Now what we have to do? Heating. On heating, what will happen? Whenever we do heating, water molecule will be removed. Then what is happening? See, this is the compound. See, NHCH3, COO, NH4 plus. On heating, water molecule should be eliminated, right? From where? 2 hydrogen from here, 1 water from here. So the remaining is CH3, CO, then the remaining is NH2 because from here 2 is removed. Got it? Same thing is here. Reacting with the first the product is this COOH group will react with the ammonia to produce RCOO NH4 plus. Whatever the R group, suppose it is CH3, it will be CH3. It is benzene, it will be benzene. From that one, water molecule is removed. So first they will produce, this is called a ammonium salt, ammonium. Okay. See, suppose you are taking 2 dicarboxylic acid, same thing. These 2 groups will convert into corresponding ammonia. Then each one water molecule will be removed. Okay. If you are doing strong heating again, here again water molecule will be removed. Then they will join together. Okay. One ammonia molecule will be removed from here, then they will join together. Got it? Yes, that is the reaction with the ammonia. Any doubt? Okay. Next, reactions involving COOH group. Now the chemical reactions involving COOH group. See, first one is reduction. I told you, whenever you do reduction reaction, we have to use a reducing agent, that is lithium aluminum hydride or sodium boron hydride. So here lithium aluminum hydride again. Okay. See, it is used to convert carboxylic acid to primary alcohol. See the reaction. No need to write the mechanism, only the reaction is enough. Okay. Diborane is difficult to reduce to functional groups such as ester, nitro, halo, and so on. Diborane. Diborane means B2H6. Okay. The carboxyl group is not reduced by sodium borohydride. Okay. Normally we are using lithium aluminum hydride, but here sodium boron hydride also there is a reducing agent, but here we are not using sodium boron hydride because they are not reducing carboxyl group. Only we are using aluminum, so lithium aluminum hydride. That is the reduction reaction. Got it? Next one is decarboxylation. Decarboxylation means it is the removal of carbon dioxide. This is the sodium salt of an acid. So if you are taking an acid, first you convert it into acid by sodium salt of acid by reacting with what is the reaction? The first reaction. We can react the acid with the metal. We can react the acid with the alkali. We can understood. So what will happen? You will get the corresponding metal salt. Means if you are using sodium hydroxide, sodium salt of acid, this one you will get. If you are using sodium metal also, you will get the same thing. So you have to do decarboxylation. The reagent used for the decarboxylation is also important. When you do the decarboxylation, CO2 will be removed. See, then the remaining will be RNA. So the Na will be replaced by hydrogen. You will get RH. This is a hydrocarbon and Na2CO3. Okay. So this is the COOH group involving reaction. Next one is important name reaction. See, Aldehydes-Zelinsky reaction. This is a halogenation reaction. Carboxylic acids containing a hydrogen are halogenated at the position using chlorine or bromine in the presence of small quantity of red phosphorus to produce alpha halocarboxylic acid. What is alpha position? What is alpha position? The carbon atom near to the functional group. That is called, means the suppose sometimes it may be the functional group, they may not contain a carbon atom. Then the functional group connected carbon, the next carbon. Got it? R, CH, COOH, bromine. So this is the alpha carbon, this is the beta carbon. But in case of some other compound like RCH2, CHBr, this is not beta or this is not alpha, because this is the functional group and this halogen containing carbon is connected to the first carbon. This is the alpha. Understood? Here, this is the alpha, this is the beta, because the functional group itself contains carbon. In other cases, this is the alpha carbon. This is the carbon containing halogen and this is the alpha carbon. This is not alpha. No. Because the halogen means the functional group is not containing carbon. Okay? Yes. So, carboxylic acid containing hydrogen are halogenated at the position using, means see, this is the carboxylic acid. So, what you are doing? First, we are halogenating the compound. Means what will happen at the alpha position. This is the alpha position. I told you, because this is the main, means the carbon atom. This is the alpha position. So this alpha position gets halogenated. Okay, this is called a Aldehydes-Zelinsky reaction. And the reagents, halogen, whatever the halogen, you have to substitute that halogen and red phosphorus. Important. Okay, that's all. Next one is ring substitution. What is ring substitution? We are substituting from the acid, we are substituting in some positions. Aromatic carboxylic acids are electrophilically substituted with the carboxyl group acting as the deactivating and meta-directing group. So this is the acid. So when we are doing nitration, nitration means we have to use a nitrating mixture. Nitrating mixture is concentrated nitric acid and concentrated sulfuric acid. Mixture of concentrated nitric acid and sulfuric acid is called a nitrating mixture. If you want to substitute the position of a particular compound with a nitro group, NO2 group, we have to do nitration reaction. So here we are taking the nitrating mixture and heating with the compound. Then what will happen? See, at the meta position, NO2 group will come. So what is ortho, meta, para position? You know, right? The position near to the functional group is called ortho. This is ortho position. This is meta position. This is para position. So here the meta position, the reaction will take, means the functional group will come. Okay. The same thing. If you want to substitute with a halogen, see, halogenation you can do. Meta position itself. Okay. Then the important thing is they are not undergoing the Friedel-Crafts reaction due to the carboxyl group deactivating and the catalyst aluminium chloride becoming attached to the carboxyl group. Okay. So they are not undergoing Friedel-Crafts reaction. The reason is also important. Got it?